No, you can just remove that. The other way. Should work. Yeah. So, good evening, everyone, and welcome to the IPA C.V. Raman Lecture on which is to be given by Professor Umesh Waghmare, who is from JNC. Before I invite him to give to tell us about his work, I would like to just introduce IPA to everyone in the audience. So this talk is simultaneously being live streamed across the country. So IPA is Indian Physics Association. It has been founded in 1970, and it has about 4,600 odd members across the country. And what are its activities? It takes out physics news, and it also organizes special lectures, seminars, etc. It has young physicists meets. It has awards in various categories. Given in this day and age of diminishing number of awards, these are some of the awards which actually remain. So, just to give you an idea of physics news, essentially you have articles on which it comes out quarterly, and it has articles covering a wide range of physics all across the span of physics. And it covers various topics also which are of interest to physicists, which are about physicists sometimes, and so on and so forth. So as you can see, there's Bose, articles on a special issue on Bose, and so on and so forth. So the IPA has several awards which it presents. They happen once in 2 years. Some of them are the R.D. Birla Memorial Award, the Murli M. Chugani Memorial Award for Excellence in Applied Physics, P.K. Iyengar Memorial Award for Excellence in Experimental Physics, Hema Ramchandran Lecturership Award for Excellence in Experimental Physics. Hema doesn't need an introduction here. S.N. Sheshadri Memorial Instrumentation Award, N.S. Satyamurthy Memorial Award in Physics, Booty Foundation Award in Theoretical Physics, Astrophysics, and Biophysics, Ashwini Kumar Rath Memorial Awards in Nuclear Physics. So the very important point to note is that the last date for the current cycle of nominations is 20th of March. So it is timely to make this announcement. Should anyone across the country have someone in mind to nominate under these various award categories, please do so. It is welcomed, and it is quite prestigious. The awards carry a fair amount of money also, if that is an incentive. So there are best thesis awards and so on and so forth. So there are a lot of, so there is this kind of activity which IPA does. Essentially, the awards are there to widen the scope of awareness among the general society, and that is one of the primary functions that they serve. So it is a worthwhile exercise. If you wish to join IPA, and even students can be members of IPA. In fact, the vast membership is perhaps students. You go to the IPA webpage, and you fill out a form. If you are a student, then you need certification from the institution. But otherwise, I mean, you can just apply. You can get a life membership for next to nothing. So please consider it. This is the executive committee for 2023-24. These are the members of the executive committee who are there. And then there are Gender in Physics Working Group that IPA has. These are some of the members. And lastly, this lecture, the C.V. Raman Lecture, has been given by several people over the years. And these are some of the prominent luminaries in Indian science. And I'm happy to say Umesh will be on this list next time. So with that, let me just spend a couple of minutes introducing the speaker. So Umesh Waghmare is a professor at JNCSR, and he has a huge body of research work. He received his bachelor's from IIT Bombay, BTech in engineering physics, and then from there on he went to Yale for a PhD and a postdoc at Harvard, and since then he's at JNCSR. In his long years at JNCSR, he has founded a company. He has garnered many accolades and awards for his work, including the Bhatnagar Award and the Infosys Award. He is also the fellow of the 3 Academy of Sciences, maybe 4 actually. So so there are 3 Academies of Sciences and 1 Academy of Engineering, and he is right now the president of the Indian Academy of Sciences. And for those who do not know, the Indian Academy of Sciences exists at that corner of the campus, and you are welcome to go and poke around and figure out more about the academy. Umesh's work is related to ab initio modeling of material systems, and he has, I will leave him to say more. So thank you very much, Umesh, for accepting this invitation by IPA to give this lecture, and I look forward to an extremely illuminating lecture.
Thank you, Sadiq. Am I audible? Okay. Thanks again, Sadiq, for a very kind introduction. I'm truly honored to be giving this C.V. Raman lecture by Indian Physics Association and DAE. I thank Sadiq and also Professor Yusuf for this invitation. And I'm even more delighted to be giving this lecture at Raman Research Institute and have chosen to talk about some recent work we have done. In fact, it's unpublished, but it's very intimately linked with Pancharatnam's work as well as C.V. Raman's work of Raman effect. Yeah? So we are announcing here, delighted to announce a new class of spectroscopies based on very interesting principles, ideas from quantum geometry, and we will demonstrate it in the context of vibrational spectroscopy, but these ideas apply to other dynamical excitations also. Yeah, so by the end of this lecture, I hope you will have a clear idea about what is quantum geometry and how we propose this new type of spectroscopy based on that. So let me get started. The title is Sensing Vibrations Using Quantum Geometry of Electrons, and in particular we will be focused on crystals here, but you will see how the flow goes. The work has been done by my PhD student, Bhuvaneshwari, who is also here in the audience today, and experimentalist Mandar Deshmukh, who sort of interacted with us to ensure that what we propose is realistic and possible to be validated in lab. The work is supported by a J.C. Bose National Fellowship and also the Department of Science and Technology. So let me get started with something very simple, and probably some of you know this, electric dipole. All of us know it from high school days. If you have a set of charges, in this case 2 charges, negative and positive charge, you can easily estimate the electric dipole moment, P, which is basically Q times distance between the 2 charges. And this is commonly used concept in molecules, also in solid state physics. But if you go to a crystal and then ask a question, what is electric dipole of a crystal? And here I'm showing you a one-dimensional example of sodium chloride chain. Basically, sodium is or hydrogen chloride chain. This is positively charged and this is negatively charged, and it's repeating from -infinity to infinity. If I choose a unit cell, which is given by this dashed box, blue box, I will get a dipole moment which is pointing to the right, positive p, same as what I had here. If I use another unit cell shown here by green dashed box, I get a dipole moment which is exactly opposite of that. Yeah? If I choose this box as the unit cell, the blue dash box, I get zero dipole moment because symmetry, the chlorine atom is at the center of inversion. So you see, by using different choice of periodic unit cell of a crystal, I get different estimation of electric dipole moment. Well, this is even more complicated because in real crystal, the electron density is not really like point charges. It's a continuous distribution, this function in real space. So where do you draw the boundary of a unit box is not clear at all. And as a result, polarization, which is electric dipole moment per periodic unit of a crystal, is an ill-defined quantity. Yeah? Such a simple quantity, we always take it for granted. Any dielectric, you make measurements in a capacitor, you change its electric dipole of overall polarization, right? But it's not well defined. Well, of course, now there is a lot of progress that has been made in this area. So let me get to that. If you ask an experimentalist, how do you estimate electric dipole moment? You will see that most experiments always involve measurement of change in the dipole moment, never an absolute dipole moment, particularly in the crystalline context. Yeah? So typically you would place your medium or a crystal inside a parallel plate capacitor, you switch on the voltage, and what one measures is actually the current that flows through the circuit. And if you integrate that current out with time, you will get change in polarization. Yeah? So that's what is measured experimentally, not absolute polarization. So bulk properties, which often involve derivatives of polarization, for instance, dielectric constant, piezoelectric constant, pyroelectric constants, these are all functional properties of crystals. They always involve derivatives of electric dipole polarization or the changes in the polarization like this. Yeah? Okay. Well, when you change external field, there is a redistribution of electrons inside a crystal, and that basically leads to flow of current. So the next concept I'm bringing in here is electric current density, which is very intimately linked with this electric dipole density of a crystal. And this current density basically is the time rate change of polarization, and change in polarization is given by just time integral of an adiabatic current, if you may call, that flows through the crystal and leads to redistribution of electrons. Okay? So this was established in 1902, or proposed in 1992 by Rafael Vesta. Well, let's now look into the quantum theory of polarization. And there also, I'll first, for the sake of students or non-experts in the audience, I'll just tell you that in a crystal, which is characteristic of crystal is periodicity and translational symmetry with a unit cell repeating in real space, electronic wave function is a block function with a form which is given by this plane wave, e raised to ik dot r, which has a periodicity which is longer than the unit cell of a lattice. And that plane wave is multiplied by something like uk of x, which is basically cell periodic function. It has the periodicity of real space lattice. K is a quantum number of electronic energy eigenfunction in a crystal. And h bar k basically is called as the crystal momentum of an electron. So when you apply electric field, this momentum will change in response to the force felt by an electron due to electric field. So with change in any generic field, lambda, let's say electric field, electronic wave momentum k changes to k plus delta k, and due to periodicity, remember psi k has the periodicity in the k space also. Wave function at k is same as wave function at k plus 2 pi by a. Yeah? So as a result, if this is the band structure of electrons, again, for those who may not have seen it before, it's essentially electronic energy as a function of this quantum number k, and it's a periodic energy function. This is valence band occupied with electrons, and red is conduction band, which is not occupied with electrons. And each electron here will basically hop from k to k plus delta k, and basically if it moves all through the band, this electron will recover its state again because of the periodicity. So due to periodicity, electron trajectory goes from k equal to minus pi by a and comes back to pi by a, and that sort of closes the loop. So Brillouin zone, this is called Brillouin zone, or unit cell in the reciprocal space lattice. Due to periodicity of the wave function, basically you close a loop when you go from one unit to next. Yeah? So that closed loop is very important because that's what will come in this quantum theory of polarization, where change in polarization delta p of an insulator with adiabatic change in Hamiltonian, which is parameterized by lambda, which is any external field, electric field or pressure field or whatever you like, can be integrated analytically. Yeah? And this work was done by Kingsmith and Vanderbilt in '93. They showed that you can actually do that integral analytically, which I showed here, and using Bloch theorem and other properties of Bloch function, and you basically get P of lambda, which is at a value of external field, which is given by this expression, where UK is the cell periodic part of Bloch function at a value of external field lambda, and this is basically a standard integral. I will explain to you what it means in a minute. And most practical calculations which calculate electric polarization use basically this formula. It's called Berry phase formula. In a minute, you will see why. And that is basically discretized in real calculations using Bloch functions. So gamma is actually the quantum geometric phase. I'll tell you why is it called a geometric phase. So let me explain. Yeah.
So all this description is true for permanent polarization also?
Yes, absolutely. Yeah.
It is induced most cases.
No. It's also, in fact, this problem was motivated by spontaneous polarization of a ferroelectric or a piezoelectric, which is in fact not measurable. In ferroelectric, it is measurable through hysteresis loop, which also is a change in polarization. In fact, there are many interesting aspects to it, which we will come to, may not be in the ferroelectrics context, but related things. I'll come in a minute. So let me tell what is geometric phase for the people who may not have seen it before. So this is a pen. Imagine that this is a vector pointing up, yeah? And Bloch function is also a vector like this in Hilbert space. So if I hold this pen perpendicular to my arm, and I move my arm up, down, without changing the angle of the pen with respect to my arm, and bring it back, you will see that pen is rotated by 90 degrees. This angle is called geometric phase, and it depends entirely on the solid angle that is subtended by the closed curve that this pen traversed in space. Yeah? So this is geometric phase. In fact, Pancharatnam did this in the context of optics long back, 1956. Very interesting creative work. And Michael Berry in '84 showed that this also applies to the quantum states, and that's where it became famous as Berry phases. So this is also known as Berry phase for that reason. But it's essentially Pancharatnam phase in the context of quantum physics. Okay? So polarization is Berry phase, and polarization is electric dipole moment. It's essentially expectation value of position operator, and so remember that it's linked to the Berry phase. Yeah, this was a sort of very important advance. I should say, clarify that this expression has been known even before '94. It was known as Zach phase at that time. Joshua Zach in Israel had worked it out in some other context. But the connection with electric polarization was established in 1993.
So I still don't understand. You are saying you apply electric field and measure the change in polarization, right?
Yes.
That's which is connected to Berry phase.
Yes.
Now, if I have permanent polarization, how one
Yeah, you don't worry about electric field. E is 0, lambda is 0, then same expression
No, I'm
applies.
saying where is the change then?
Okay, in the permanent electric dipole polarization, you cannot measure it, for example, zinc oxide, which is a wurtzite lattice. Okay, there you will always measure change in polarization. If it is lead titanate or barium titanate, which is ferroelectric, the permanent polarization is measurable again as a change in the polarization. P and minus P are the two states in the hysteresis curve which you measure. And that's what is calculated here as well.
So whenever you measure change by applying some field or
Yeah.
something like that,
Yes.
so that means you always measure change only, right?
Absolutely. That's what I made it clear. Measurement is all.
Permanent polarization can't be measured.
No. Except in ferroelectrics, where I said you have two states of the ferroelectric which have opposite polarization, and you measure change between those two states. And that's how you estimate P, which is half of the difference between the two states, P and minus P. Absolutely. So please note that this is not a theorist imagination. In fact, what can be measured can typically be calculated, and that's how it is being calculated here in the context of polarization.
Why, so it's like a expectation value of something.
Yes.
So why is it called quantum geometry?
Well, it's this, okay. So this integrand is the Berry connection, okay? And I'll come to that in more detail soon. And this is the typical expression of a Berry phase, where K is the adiabatic parameter, which goes from minus pi by to I to pi by A. And I explained to you, because of periodicity, it's a closed loop in reciprocal space. And that's why it's called Berry phase.
So I have, sorry, one trick.
Yeah.
So if I have permanent polarization, then I have listed some probe to see any effect of that polarization in the change in the probe device, like input probe current or something. So why can't I measure permanent polarization?
Okay, I'll explain to you. I have tried explaining to you that nowhere you can measure permanent polarization. The specific things I can certainly explain to you. But take my word for now, and we'll clarify further. Yeah. And the simple mathematical answer is X is not a periodic operator, so you can't really get this expectation value in simple way. Yeah? Okay, so just to summarize what we learned so far is you have polarization pointing up here, and measurement of polarization involves flow of current, and that's linked to Berry phase, or what is called as geometric phase. So three ideas have been brought out, and they're all intimately linked with each other, which is what you will see will translate into as we go along through this talk.
If you want to say the change in polarization is related to change in geometric phase, or just
Yeah, well, I show you that polarization is geometric phase in
change
this.
in polarization?
No. See, this is defined at a specific lambda, right? So change in polarization is change in polarization at lambda equal to L and lambda equal to 0.
Yeah, but
So for permanent polarization system, if you have a state with zero polarization, which is centrosymmetric state, you can estimate absolute polarization using this formula again.
sorry, I wanted to say that you can only measure change in geometric phase, like the way you are.
No. Geometric phase is calculated absolutely.
If I can measure, then I measure.
See,
direct-
geometric phase, because it's a phase factor, is defined modulo 2 pi. But otherwise, you can calculate it at any.
The geometric phase.
Yeah.
So I'm saying from there we can measure polarization.
No, the point is, when you want to interpret geometric phase as a measurable polarization, you need to be careful. Yeah? So anyway, I think that's a subtle point. In fact, in many materials, I will show you that because of this subtlety of polarization, in many cases, interpretation is not as simple as you think. Okay. So these three ideas are linked together. We will link them to even more interesting ideas in the coming slides. Okay, so let me get going. What about geometric phases in 2 dimensions? Right? In 2 dimensions, you have kx and ky as the coordinates in reciprocal space, and this is the unit cell in reciprocal space. You can calculate Berry phase gamma x, which depends on ky, and likewise gamma y depends on kx. So the Berry connection, which I defined earlier, is a vector quantity now, And you can also define Berry phase along any closed loop using this cyclic integral. And Berry curvature is basically reciprocal space curl of Berry connection, which is defined here. And gamma alpha, alpha being x or y, are related to the expectation values of x and y, position operators. Yeah? Okay. So when you apply electric field, now this is where I think the very important concept is coming up. If you apply electric field along x direction, right? Semi-classically, you can expect that the crystal momentum will change of an electron will change along x direction. So electron will go from here to here. Yeah? And on this axis I'm showing you, on the x-axis is momentum h bar kx. Electron is here. Due to applied electric field, it moves from here to the next point, px plus delta px. When that happens, if gamma y changes, you know, gamma y is the position along y direction. If that changes when the momentum changes from kx to kx plus delta x, you get basically velocity which is perpendicular to the applied electric field. This is the key concept called anomalous velocity. Because if Berry curvature, omega z, which I have defined here, is non-zero, it will give rise to drift along y direction because the Berry phase is changing along y, Berry phase along y direction changes when the electron moves along x direction. Clear? If that happens, you have a Hall effect with no magnetic field, no external magnetic field. All right? So this is a very important idea. I hope that is clear to you. And it's essentially linked with the fact that y expectation value, which is the Berry phase gamma y, changes as a function of momentum of electron along x direction, kx. And that change is captured by omega, which is the Berry curvature. Okay, so geometric phase and you will see it's linked to what is called as anomalous Hall conductivity. If I have a metallic state where this contour defines a Fermi surface, meaning electronics quantum states inside this curve are occupied, outside the curve are unoccupied, and if I do calculate the Berry phase phi along this closed loop, you can show that actually that gives you off-diagonal conductivity sigma xy, means electric field is along x direction and current flows along y direction. Yeah? And that's basically Hall effect. And that's why it's called anomalous Hall effect, because there is no external magnetic field. And this non-zero sigma xy comes about because of the non-trivial Berry phase, and that is essentially because you have Berry curvature, which is non-zero. Yeah.
So the non-trivial phase comes about because your block states have the property that
exactly
depends on kx.
Right.
So do you get that without applying some effective magnetic field to the system?
Yes, it is with zero magnetic field, absolutely.
No, if you have just a tight binding model, I probably.
Yes, yes, of course. Yeah.
I mean, so when would you have?
I'll come to that. You will, yeah. When is it measurable? Your question is, how will you have measurable consequences?
No,
Or
I mean, what is the single particle? What is the potential for the single particle for which you
okay. Any insulator will have some variation, but omega has to add up to non-zero to get this effect. Yeah. So the answer is yes. Any model you use will have non-zero, very weak values of Berry curvature. You can try it out with your favorite tight binding model. In fact, I'll come to that in a minute in graphene, where it's analytically calculated. Okay, so what we define here is using these concepts of Berry phases and anomalous velocity, transverse velocity, one recovers what is called as anomalous Hall conductivity.
Quantize that quantity for any system.
You will see. Yeah, just hold on, please. Yeah. Okay. So if I have an insulator, so we don't have a Fermi surface anymore. You have a Brillouin zone or unit cell of a reciprocal space lattice. In this case, you will calculate Berry phase over the whole Brillouin zone because all the states are occupied. And in this integral, if you calculate it, it's actually integer. And that's called as Chern number. So responding to your question, this is quantized. And it's integer, and Hall conductivity associated with this is integer times this E squared by h, the fundamental unit of electrical conductivity. Yeah. So, of course, what this means is the equivalence between the states at these two edges is no longer valid if the Chern number is non-zero, and as a result, time reversal symmetry has to be broken if one wants to have Chern insulator. Any 2D system like this, you want to have non-trivial, non-zero Chern number, it has to be broken time reversal symmetry. Okay? We'll see all this. These are getting even more and more interesting as we go along. So just hold it. Yeah, wonderful. So these insulators are also called as quantum anomalous Hall insulators because they will also exhibit Hall effect, which is quantized if the Chern number is non-zero. Although they are insulators, and the Hall effect is basically contributed by the edge states which carry current in these cases. Wonderful. Well, not many materials are known to be Chern insulators because of the obvious condition of broken symmetry and as well as non-trivial geometric curvature, Berry curvature. So there was an introduction of what is called a Z2 topological insulator, where basically one calculates Chern number for upspin and downspin separately. And what you can show is because of the time reversal symmetry, they are equal and opposite, so they add up to 0, as you will expect from time reversal symmetry. But the Z2 invariant, which is the difference between Chern number of upspin and downspin, is odd, and that needs, of course, spin orbit coupling. So coming back to your question about, I'm showing you gamma x as a function of ky. This is what you had asked. For a normal insulator, you will see the variation is slight but boring, means it has basically 0 integral. Whereas in topological insulators, Z2 topological insulators, for spin down, it goes this way, and for spin up, it comes the other way. You know, so the overall Chern number is 0, but the difference between up and down spin is non-zero. Yeah? So these insulators are called as quantum spin Hall insulators. These are the ones which became very popular in the last 20 years, thanks to Kane and Melee work from University of Pennsylvania, along with Liang Fu. And these exhibit what is called a spin Hall effect, okay, not anomalous Hall effect, as I explained. Okay, so the ideas that I introduced to you, I will summarize now. They are all intimately linked with each other. I started with simple polarization, and I told you, you know, it gives rise to surface charges. This is linked to Berry phase, and of course the electric current. And now, knowing these, we showed that if you have non-trivial geometric curvature of electronic structure, they give rise to anomalous Hall effects and also non-trivial electronic topology. And topology is characterized by 8 states, which are essentially intimately linked with surface charges in polarization. So it's one single unified picture which captures all these ideas in a physically meaningful manner. Yeah.
So, in the beginning slide, you showed this step where, like you said, that depending on how you choose your image set, you get this different polarization, so that it's not ill-defined quantity. So suppose I now perturb this initial system, like the space between the thing I perturb. So and choose one convention and measure the polarization. So is it independent of the convention?
Yeah. No. You just don't get a single answer.
No, but I want to do, because now I am measuring the change in the
Yeah, it's not. So simple answer is, if you have,
change in the polarization is not
no. Sorry?
No, change in polarization is
No.
unique.
Not from charge density. See, the clean message I'm giving you is distribution of charges in real space or even wave functions. Unless you resolve to Berry phase approach, you cannot estimate even change in polarization.
Let's think experimentally one is measuring change in polarization.
Yeah. No, you are measuring current. If you calculate current from your density, you can estimate the change in polarization.
You're saying that change in polarization is also ill-defined quantity.
Is what?
It's also ill-defined quantity.
Yes. If you work only with charge density. Yes. Absolutely. Even, see, Berry phase approach doesn't solve the problem fully. It still preserves that ambiguity, but it says the ambiguity is always on quantum polarization, ER, essentially, R being the real space lattice vector. Absolutely.
But so how do you define polarization?
Okay.
Talking about changes in polarization.
Yeah.
How do you define? Do you not define it in position space?
No.
Okay.
No, the answer is no. You can do what is called as one-year orbital projection to sort of derive charge centers, essentially derive point charge picture of, it's essentially a problem of how you partition your charge density. Yeah? If you can partition it in a meaningful way, then changes are possible to estimate it. Otherwise, it's ill-defined. That's what was my response to you. Yeah, anyway, I will certainly be happy to convince you these are rock solid ideas, very well established. There's nothing uncertain about it, and it takes little time to understand the deeper aspects of it. So, okay, so these are all concepts which came from very simple puzzle that I started out with, essentially the polarization puzzle. Okay, so whatever we learned so far, on the left column I'm showing you the quantum geometry of electrons and various concepts we learned. One is the Berry or Pancharatnam phase. It's linked to the Aharonov-Bohm phase in electromagnetism. Berry connection is linked to vector potential in electromagnetics. Berry curvature is essentially magnetic field strength. And the Chern number that I defined is related to the Dirac monopole charge as an emerging electromagnetism. So these geometric features of electronic structure give rise to emergence of these electromagnetic fields which govern motion of electrons as a consequence of quantum geometry rather than real electromagnetic fields. Yeah, that's the take-home message. So let me now go to an example which is much easier to relate to, and this is called Valley Hall effect, a concrete example where these ideas beautifully apply. And this is the example of graphene, which I'm sure all of you have seen before. There are 2 carbon atoms per unit cell given in these 2 colors. And this is the electronic structure, particularly at the Fermi energy. You will see one has linear dispersion of bands known as Dirac cone. In a normal semiconductor, bands have parabolic dispersion as a function of momentum. As you will expect, classical particles, energy is p squared by 2m. Whereas in graphene, this linear dispersion essentially means you got to start from relativistic expression of energy and set mass to 0, you will basically get E equal to Pc, except for the fact that in this case, velocity of light is replaced by Fermi velocity of electrons in graphene, okay? So this is to show you that electrons near the Fermi energy of graphene behave as massless Dirac fermion particles, okay? But that's not most interesting about graphene. Yeah, this is, of course, interesting for some who wants to study relativistic effects. But the Berry phase associated with electronic states, if you go along a closed orbit in this Dirac cone, you recover a phase of pi. Yeah, and that gives rise to chirality of electrons associated with a given Dirac point. And that means electron rotating along this orbit feels as if there is some fictitious magnetic field associated with it. And because chirality is conserved, electrons in graphene have very high mobility. Yeah, so that's why, although it's zero gap, zero electron density at the Fermi energy, it has extremely high mobility associated with it. So to summarize, Berry phases in graphene are shown here. This is the hexagonal Brillouin zone of graphene. There are 2 types of K vectors where you have Dirac points, K and K prime, and the Berry phases there are pi minus pi alternating like this. Okay, so you can differentiate between the K and K prime valley by the Berry phase that is associated with electrons in that Dirac point. Yeah, so that's what is to be noted here. Unfortunately, at this stage, it's not a very usable thing because there's only one state at the Dirac point which has non-trivial Berry phase or Berry curvature. So to access exotic physics in graphene devices, one needs to open up a band gap at the Dirac point by breaking inversion symmetry. And if you do succeed in that, what is the physical consequence of this, which is very fascinating, that the 2 Dirac points of graphene behave as if the electrons in those 2 points have opposite magnetic moment. So if you apply electric field and the electrons move upwards in response to this electric field, one valley populates one side and the other valley populates the other edge of the graphene nanoribbon. So if you do an experiment like this, the electrons move this way, you have valley separation. You mean you have, this is what is called as Valley Hall effect. And the topological Chern number associated with it is called as Valley Chern number, which is basically Chern number for valley K minus Chern number of valley K prime, which is equal and opposite, so you get a non-trivial effect. So this gives rise to valleytronic devices. You will ask, how do we access this experimentally? Because there is no voltage which gets developed in this Hall voltage which gets developed, because both are negatively charged electrons. Yeah, so to differentiate between valleys, you have to use circularly polarized light to excite electrons selectively, because the chirality in the two valleys is opposite. And that's how one can access it. But this is a very simple effect I can demonstrate as a consequence of just this interesting quantum geometry. Okay. So let me now summarize a few other constraints that we have, why these are not commonplace. Yeah.
How is the gap opened up?
Okay, you can just put hexagonal boron nitride on top of graphene in AB stacking or any stacking. It opens up a gap, a small gap. Yeah. I'll come to that in a little bit, actually. Very interesting features. Okay, so consequences of symmetry. The reason why these are not commonplace yet is because time reversal symmetry means omega Berry curvature is odd, inversion symmetry means it's even, and in centrosymmetric non-magnetic systems, it means Berry curvature is identically zero. It's zero at all k vectors, and which means most metals are centrosymmetric, and if they are non-magnetic, you won't see these effects at all. Silicon, many other materials are centrosymmetric and non-magnetic. These quantities will not be visible at all. Okay? So there are some very interesting development recently. It's called nonlinear Hall effect. And basically it's called anomalous linear Hall effect, which is governed by the conductivity I defined. And that requires you to have broken time reversal symmetry. But what was shown in this work is if you apply electric field in x direction, the Fermi surface in the system displaces to the right or to the left, depending on the direction of field. And when that happens, the applied electric field lowers the inversion symmetry and shifts the Fermi surface, creating asymmetry in the occupied states. So although the Berry curvature may be symmetric, you create asymmetry in the states which are going to contribute to your integral. And that can give rise to, for example, first moment in reciprocal space of Berry curvature, which can be non-zero. And this was a theoretical prediction by Inte Sodeman and Liang Fu, which showed that the D, which is the Berry curvature dipole, a new quantity I'm introducing here, which is essentially first moment of Berry curvature in reciprocal space. If that is non-zero, one generates either rectification or second Hall effect, meaning the Hall current Jy is a quadratic function of Ex squared, times Berry curvature dipole. Means you apply electric field at a frequency omega, Hall effect arises at 2 omega or 0 frequency. Yeah? So this is the take-home message, and this is very nice because this lifts some of the symmetry problems or constraints that we had earlier. In fact, this was predicted in 2015, and in 2019, this was demonstrated experimentally at MIT, showing that if you have in this case, it's tungsten telluride, which is a type 2 Weil semi-metal, which has non-zero D, the Berry curvature dipole. They call it lambda in this paper. But if you show, if lambda is non-zero, basically you develop a nonlinear Hall effect. And this non-zero lambda comes from the fact that you have opposite Berry curvature in the two valleys, which are at k and minus k. And if you do that, what is interesting is the linear Hall effect always has a current which flows at an angle, because at a frequency omega, you have a current in x direction as well as Hall current with the same frequency. So it's at an angle. But in nonlinear Hall effect, the beauty is the signal is exactly perpendicular because there is no second order effect along that longitudinal direction. Yeah, so that's the advantage of nonlinear effect, although it's a weaker effect. Yeah, so you get this beautiful nonlinear effect, and they demonstrated it nicely in this paper experimentally. So nonlinear Hall effect says that you can still have time reversal symmetry and see this effect. But unfortunately, the band gap of the material has to be small to get non-trivial Berry curvature. And lastly, the crystal symmetry has to be low. So although it is more common than the anomalous Hall effect, it is still restrictive in that sense. So this is where we started our work. And basically, Bhuvaneshwari looked at monolayer of tungsten telluride and used quantum calculations to show that you have a Berry curvature with a dipole moment or first moment in reciprocal space because of the specific mirror plane. And the mirror symmetry basically means the crystal should have only one mirror plane. It has two mirror planes perpendicular to each other, you get zero dipole moment again. Yeah? So still, for this effect also symmetry is a constraint. So the question we asked is, can we break this symmetry dynamically? Statically, you don't have much choice. Crystals are what they are. So dynamically means you can use vibrations, or you can use other dynamical excitations which can lower the symmetry. So what we proposed is the Berry curvature dipole can oscillate in time with the frequency of your dynamical excitation, omega naught. And these can be vibrations, for example, and a vibration will change, induce Berry curvature dipole, provided the first derivative of Berry curvature dipole with respect to vibrational amplitude is non-zero. Yeah? Just to remind you, Raman effect is where first derivative of polarizability with respect to vibration is non-zero. Here we are proposing Berry curvature dipole. Like an infrared spectroscopy, if the electric dipole first derivative with respect to phonon is non-zero, phonon is polar and IR active. Here it's the topological or geometric feature of a phonon. So this defines the selection rule for the spectroscopy that we are introducing now. And indeed, if this is non-zero, what we work out is, again, very simple mathematics. You get Hall effect at twice the frequency, like the nonlinear Hall effect. The first term is exactly what Liang, Fu, and Sorendin showed. But the second part is what we are proposing. And that depends on the derivative of Berry curvature dipole with respect to phonon. And you will get peaks at these various frequencies. These are operating frequencies, AC frequencies 2 times omega AC. And it will be modulated with plus omega and minus omega. And you will also have, because of the rectification, at peak at omega naught. Yeah? So even centrosymmetric system, non-magnetic system, in our proposal can have non-trivial Berry curvature induced, because dynamically one can lower the symmetry.
So what are the frequencies, omega naught and omega?
Omega naught is the frequency of vibration, and this is omega naught, and omega AC is going to be the operating frequency. As I showed you in this experiment, the longitudinal voltage applied is basically the applied frequency. Any Hall measurement, it's an AC Hall measurement. Yeah. So indeed, what we propose is these ideas will apply to fairly high symmetry crystals, fairly and time reversal invariant system, where these earlier ideas wouldn't work. So the present work, I'll just tell you, I won't go into methodology here. These are based on very state-of-the-art, accurate first principles theory and simulations. They use density functional theory for the quantum motion of electrons in a crystal and obtain electronic structure and interatomic interaction, hence phonons, from scratch. So we have basically no experimental input in our analysis that I will present in the next slides.
So in the previous slide, omega naught is set by the system. So,
Omega naught is the vibrational frequency of a system, yes.
so it doesn't have a spread of frequencies of vibration.
Okay, so this is a very strong condition. Any crystal has infinitely many vibrations, and so in Raman you don't see all of them. In Raman you see only the phonons with the long wavelength limit, and the same applies here as well. Yeah. Okay, so all this is captured in our calculations fairly well. So let me first show you an example. This is centrosymmetric tungsten telluride monolayer, which shouldn't show any nonlinear Hall effect that I explained. And what we show is there are two phonons I'm pointing out. This is phonon spectrum of monolayer of tungsten telluride. One is the optical BU phonon, and one is LA phonon, which is the longitudinal acoustic mode, or it essentially is a strain wave in the crystal. And what we show is both of these phonons are active in terms of QGUES, we call it GQUES spectroscopy, and basically the Berry curvature dipole becomes non-zero moment you freeze in these changes in the structure associated with these vibrations or the strain mode. What it means is these phonons, I'm showing you displacement of atoms involved in these vibrations. This is optical mode, this is longitudinal one, the strain mode, and they will have non-trivial signatures in nonlinear Hall measurements. That's the prediction. Indeed, the specific experimental setup we propose is you can have a Hall measurement where you apply AC electric field along these two electrodes and measure nonlinear Hall effect along these two electrodes. Yeah? If the frequencies are high in terahertz, you will not be able to do the Hall measurement in this simple way. You have to use terahertz spectroscopy to detect the emitted radiation. So you have a Hall type circuit, but instead of measuring Hall voltage, you measure the emitted radiation. So we call this is emission mode, and this is called circuit transport mode of the spectroscopy. And if you do that, we have very specific prediction for monolayer of centrosymmetric WTE2 and non-centrosymmetric structure as well. You have a peak at the LA phonon frequency. This is like IR spectroscopy now, because Berry curvature dipole is basically absorbing that phonon. You get a peak at the phonon frequency of 3.2 gigahertz. But you also have Stokes and anti-Stokes peaks now, which are associated with the applied frequency. They are basically omega, 2 times omega AC plus minus omega naught. For optical phonon, you will see there is a central peak which is associated with the frequency of the phonon, and then two side peaks, and the difference between these two frequencies is exactly 2 times the applied AC voltage. Yeah? So if you now, the beauty of this is similar to IR as well as it's similar to Raman. You have Stokes, anti-Stokes, and you have the central peak as well, which is the vibrational peak. More than that, you can also have a possibility to translate signal from gigahertz frequencies to terahertz frequencies. So frequency modulation technology can be developed basically using these ideas as well. Okay, so these are specific predictions which we hope experimentally should be able to validate. Of course, the exact location of peaks will not match experiment within, but we expect them to be within 5 to 10%. So our idea of dynamical lowering of symmetry works. And based on that, we introduced a new type of spectroscopy. However, these ideas are also still restrictive because you need to have a narrow bandgap semiconductor for this. And that we haven't solved yet. And as a result, we can use these ideas only for the crystals which have non-trivial quantum geometry. So it's still very restrictive because many of you would be disappointed. Look, we work on these very interesting semiconductors or other oxides which don't have this quantum geometry. So we overcome that problem by showing that if you interface your inert material, boring geometry, quantum geometry, and interface, for example, hexagonal boron nitride. I think someone asked me earlier. You interface it with graphene. Graphene, I explained to you, has some potential quantum geometry. You can combine the merits of both of them. So you can measure frequency of HBN by using quantum geometry of graphene, which is the substrate. And that's what we show here. This is hexagonal boron nitride, and these arrows show you the displacement of atoms involved in a specific vibration. And for that vibration, we show that actually the Berry curvature dipole is induced in this heterostructure. And this dipole, Berry curvature dipole, is hosted in graphene. Yeah? And using this now, we can propose an experiment which involves graphene and hexagonal boron nitride deposited on it, and you shine laser light. In this case, the laser light that we propose is at a frequency 2.52 terahertz. This choice is based on the fact that you do have commercial lasers available at this frequency. I remind you that terahertz frequencies or even IR are not so easy to work with experimentally. Yeah? So we have put in some effort in figuring out which specific commercially available equipment can be used, and in this case, it's this particular laser from Manchester, and that can be used basically to study this system, and these are the predictions we have. In fact, you have one peak which is associated with the E vibration, which is at 41 terahertz, and then you have two other peaks which are Stokes and anti-Stokes peaks associated with the fact that energy is pumped in from 2 times omega AC. That's basically the 2 times omega light now. because that's the pumping frequency in this kind of experiment. Okay, so the same ideas can be, I'm almost getting over time, so I'll close now with this slide. We use these ideas now in WTE2. You have laser light at the same frequency, 2.52 gigahertz, and you have tungsten telluride. You will see there are many peaks coming up now in the spectrum, and basically these 3 peaks are omega 1, omega 2, omega 3. These are the quantum geometry active phonons of tungsten monolayer WTE2, and they are like the infrared mode spectroscopy. But associated with them are also Stokes, anti-Stokes, similar to Raman, and those have been also pointed out. So we believe that this spectroscopy is actually quite powerful because it captures not only complementary information, it captures these 3 spectroscopies, Brillouin, Raman, and IR spectroscopies in one go. And I mean, if successful, of course. And so there is also, whatever we did so far is a classical analysis. You can also do quantum mechanical analysis similar to what you may be familiar with Raman spectroscopy, except for the frequency of light. We have AC frequency used in a circuit which can be used for pumping and down pumping. And this is basically the transport mode of spectroscopy, where this is the ground state of electrons. These are vibrational excitations. And this is the virtual state where one electron gets excited, and it can jump into the next vibrational excited state. Okay, in the emission mode, basically, it's like IR spectroscopy. One goes from the electronic ground state to vibrationally excited state and come back, and as shown here. So all of these are possible within this simple picture within quantum theory. So let me summarize my talk now. We introduced GQuest vibrational spectroscopy in 2 modes. One was the Hall transport, and one was Hall emission mode. In one, you will measure Hall voltage. In another, you would measure emitted radiation in terahertz frequencies. This can be generalized to other dynamical excitations. In fact, they will become even more interesting because magnons and that type of excitations break time reversal symmetry as well. So you don't have to go to nonlinear Hall effect. You can do it at even linear Hall effect as well. And quantum geometry ideas now seem applicable to wider set of systems as opposed to earlier situation or status where only few very premium systems were accessible in exploration of quantum geometry of electronic structure. I'll thank my student Bhuvaneshwari and Mandar Deshmukh for various interactions which led to this work. And thank you for your attention, and I'll be happy to take questions.
So if you could go back to the slide where you're showing Stokes and anti-Stokes line along with the, so I'm trying to understand the role of the pump frequency omega L. Maybe
Yeah.
in the previous slide where you just, this one.
Yeah.
Yeah, so if I think of reducing the pump frequency, omega L, then the gap will reduce between the 3. And so if I sort of think about taking the limit omega L going to 0, I mean, it looks like the central line is still there.
Well, it will go to 0. The heights will go to 0.
The heights will go to
Yeah.
0. Okay, I see. So it's, so I was thinking, so that because the central line is already there, why do you need it to be AC? The heights you're saying also depend on the frequency.
No, okay, so this is really linked to the Berry curvature dipole, which basically promotes the interaction between a pump and vibration, pump field and the vibration. If that is non-zero, then this is possible. And then you are forced to have the central peak as well. The central peak is associated with rectification, basically.
Yeah, but if I take omega L, if I reduce omega L, make it smaller and smaller,
yeah,
then the central peak still remains, but you're saying the signal strength
yeah,
goes down.
yeah, that's right.
Okay.
I didn't get into other technical details of lifetimes of phonons and coherence of vibration. So they are the physical factors which will kill those things at low frequencies. Yep.
So going back to this question about again defining this dipole moment. So if I just multiply the charge density with the position vector and integrate over the volume, that will not give a unique
No,
definition
no,
of
I
the,
encourage you to try it out.
because that's a well-defined quantity, right?
No,
I
no,
mean,
it's not. I'm telling you, it's very
No?
well established. It doesn't, and I gave you the mathematical reason for it. Is basically position operator is not a well-defined operator in the Hilbert space you are operating.
But what about in the classical systems? If I want to define
Classical system, if you have a charge neutral finite system, it's well defined.
Okay, but suppose I have there's some charge,
Not
neutral,
periodic.
not periodic,
Yeah.
not periodic,
Yeah.
and I just multiply the charge density with the position vector and integrate over the volume,
Yes.
right? That should be the
For a finite neutral system, yes, that should be fine.
okay.
Yeah.
So you're saying that when you're taking the system size to infinity is the
Yeah.
problem.
Or on a periodic structure, it's
But
not.
your all definitions are a periodic system, right? Because otherwise there is no billion or k, even for the Berry phase, all those things.
Yes. All my calculations assume no surface.
Sorry?
All the calculations or theory I presented assumes no surfaces, except when I
So
talked
PVC.
about topology, bulk boundary correspondence.
No, so I'm saying all of them are in on using PVC, right? Periodic boundary.
Yes.
Yeah. So then, why you are saying for polarization you don't think PVC?
No, no. His question, maybe you didn't hear him.
No, he
His
was
question
ask-
is, if I have charge density
Mhm.
associated with a system, can I calculate polarization?
Yes.
And my answer is no. But if he changed his question to a finite system and a charge neutral system, then the answer is yes.
So are you saying if I have a ring and I define that charge density, I can't calculate polarization?
No, it's not unique. Try it out. But this is almost
No,
30 years.
No. I am
Yeah.
saying that now, when you was looking those connection like P lambda minus P0, lambda 0, equal to let's take Berry phase change, because that is the formula you used, right?
Derived.
Or derived
Yes.
or used.
Right.
So there you can't even calculate or relate directly P lambda with the Berry phase at lambda, or are you trying
No,
to
that's
relate
what
that?
I related.
No,
Maybe-
why? Because the difference cannot be just like individual quantity.
Okay, see. I'm
Yeah,
again
that
telling
slide.
you that.
Yeah, this one.
Yeah, very good. So please note that
Hmm.
it's this difference, and if you use a state which is centrosymmetric, then almost certainly you can calculate this as a state-defined quantity at a given value of lambda.
Yes, and then I'm trying to say that you write where P lambda that formula.
Yeah,
So I'm saying that formula cannot be also unique, that right side.
I said this doesn't solve the problem, but it's modulo quantum polarization, it is unique.
So modulo means there is a change, it means there is a value, arbitrary, right?
There is arbitrariness, which is integer times quantum polarization, and most physically measurable polarizations are much smaller than that quantum polarization in normal systems. So as a result, you can still use this formula to estimate polarization. But that's when I said that if you have a non-trivial system, like topologically non-trivial system, this interpretation breaks down.
So in non-trivial system, P lambda cannot be uniquely related to that right side.
No,
quantity.
P lambda is still linked in the manner I have shown within the proportionality factor. But when you want to interpret it as a measurable quantity, you need to be careful.
Yeah,
Which
that's-
branch of the multi-valued function you belong to. That's all.
Yeah, so that's what exactly I'm also saying. That means the difference in polarization will be related to difference in that quantity.
Yes,
Okay.
yes, that's right. But that's, of
But
course.
that,
is-
then I have also further this question, and that is where the problem even in that quantity. Geometric phase is a measurable quantity or is a gauge invariant quantity.
it has two parts. One is gauge invariant, which is measurable part, and it has gauge dependent part, which is integer quantum polarization. And that ambiguity cannot be eliminated in this calculation.
More questions?
I have one more.
Well, let's do that.
So you had discussed the experimental feasibility of your very interesting prediction on a particular experimental system. So do you anticipate that there will be more experimental systems where these can be verified, and whether the signatures will be different, and so how do you anticipate?
Yeah,
this?
no, each system will have a unique signature because that's what is also Raman, right? Vibrational frequency is the fingerprint. But the scheme behind the signatures is what we have proposed if you use this nonlinear Hall type spectroscopy. So we are now in the, we think it should be applicable to lots of systems, particularly if you use the second idea we proposed, that you have a non-trivial quantum geometric substrate and you deposit an inert substrate on top of it. Vibrations of, it's like surface enhanced Raman scattering, but in that the mechanism is very different. Here, you use the quantum geometry of the substrate, but vibrations of a adsorbed system. So that will really widen the scope of its applications is what we believe. And in fact, it makes quantum materials important in this sense that they can be used in spectroscopic measurements.
So, like that quantity gamma, it also depends on the band, right? Gamma depends on the band.
So, since this is a general talk, I didn't have a band index, but it's generalized to non-abelian Berry phases. Yeah, when you have multiple number of bands, and all these I can give you
No, I have a question related.
Yeah.
So, like this is a bulk topological invariant, which you are trying to relate with all the measurable quantity, right? So, like this Berry phase or Jack phase, whatever you call, it's a bulk invariant. Now there are others also, like winding number. Like you also introduce Chan number some cases.
That's essentially winding number.
Yeah, so for example, winding number is generally independent of band indices.
You basically sum over all the bands.
No,
okay, in the single electron picture, you would sum up all the bands.
Yes, winding number is unique. There is no, like, for each bands, you have different winding number, right?
Okay, that's a technical point. Let me explain that when you have more than one band which cross each other, right, you cannot treat them as one band at a time. You have to treat all of them together because adiabatic evolution of this set of bands cannot be continued because they cross each other.
No, I'm thinking there is no crossing.
Then it's too boring now.
No, I'm
Then you can define both Chern number band wise. If there is no crossing, everything I said here applies there in a very boring way.
I'm asking that also, is it possible not using this one, but winding number to relate all those things?
This will give you the same answers. Yeah, I think it's up to what method you want to use to estimate these numbers. But Chern number is basically linked to the winding number of these quantum states. It gives you the number of edge states that you will get. So if bands cross, you have to use non-abelian formalism. If bands don't cross, then whatever I say here applies essentially in a straightforward way.
And, okay, maybe I'll ask you later.
More questions? Students? Yes?
The effective mass of electron at the graphene, which goes to zero, which results in the previous slide.
Yeah.
So this m is zero. So is it the effective mass?
No.
Like explain it a little.
No. So M is, so what we are doing is we are starting with a moving particle in a relativistic framework subjected to no external potential, and its energy is going to give you linear dispersion with momentum if you set mass to zero. In the band, you have a linear dispersion, right? Energy is exactly given by Fermi velocity times momentum of electron in a graphene. So the momentum k equal to 0 is this point with reference to the capital K vector.
Any more questions? Okay, I'll ask you one then, and then we close if there are no further hands up. So you proposed, at the very end, you proposed a set of, a methodology for doing spectroscopy. And the spectroscopy is going to throw up some signal. How are you going to distinguish the signal which is coming through the mechanisms that you have talked about from whatever else comes out?
Yeah, very good. So certainly, if you are thinking of Raman in comparison with this, in Raman, the Stokes and anti-Stokes are centered at 1 times the frequency of pumping field, omega L. Whereas in our case, they are centered at 2 times omega L. So they have totally different frequency range.
Yeah, but I mean, the question actually is how crowded is your spectroscopy going to be, and what is the resolution? I'm just asking a very practical question.
Yeah. No, so even in Raman spectroscopy or any similar spectroscopy, Sadiq, if you have a new system, it's not always simple to assign which vibrational modes they are.
Exactly.
Right? So in our system, I mean spectroscopy, definitely you will need theory to complement that interpretation, and which is needed in Raman as well, right? Because particularly if you have a low symmetry crystal, you have too many Raman active modes and it's hard to tell. So indeed, in our case, the advantage is, at least if the probing frequency, 2 times probing frequency, is lower than the vibrational frequency, then you can actually modulate it very beautifully, right? So
the experimental strategy would be you would look for a place where it is relatively clean, and then probe with a frequency so that you will get your Stokes anti-Stokes partners at in an otherwise uncrowded
right. No, but even regime. If you have a crowded one in the scheme, in Raman, at least in most Raman spectroscopy, frequency of light is the center point for Stokes and anti-Stokes. In our case, at least when the frequencies are low, vibrational frequency is the center point. So by changing the probe frequency, AC frequency is very easy to change, you can modulate Stokes and anti-Stokes beautifully and really pinpoint which is the vibrational peak. Okay.
So all the best with this adventure that you are on. Are there further questions? If not, we close this IPA lecture, a C.V. Raman lecture, and I invite you all for a high tea downstairs. Thank you. Thank you, Umesh.